So before starting with the subspaces, try one question from vector spaces. This question was from December 2016 exam. Part B. Which of the following set of functions from R to R is a vector space over R? S1 equal to F such that limit x tends to 3, fx equal to 0, S2 f such that limit x tends to 3, gx equal to 1, S3 equal to h such that limit x tends to 3, hx exists. A part, only S1, B part, only S2, C part, S1 and S3 but not S2. All the three are vector spaces.
It is C option, S1 and S3, not S2.
Yes. Reason?
Reason being the closure property. If I add fx and gx, 0 plus 0 to 0 आएगा ना. But in case of S2, it will become 2. And in S3, if limit fx exists, then if we take another function gx again, the gx plus hx also exists. The sum of the limits exist. So S2 will
In
not
S2,
be vector
closure
space.
property also fails. And additive identity is not present. 0 is not present. Additive identity is present. Sorry, absent. Vector subspace. Do you remember the definition of vector subspace?
Not really.
Okay. Let VF be a vector space let W be subset of V. W is subset of V. W is said to be a vector subspace of V if W is itself a vector subspace. Itself a vector space means if I have a vector subspace, if I have a vector space, then W is a subset of V over the field F. If W is also a vector space, then it is known as vector subspace. Means all the properties of this vector space V will be there in this vector subspace W. For example, irrational over real. Is this a vector subspace?
Yes, irrational over real. No?
Hmm.
So irrational is a subset of real.
Yes, it is a subset of real.
So it is also subspace because real is a vector space. So it will satisfy all the properties.
But I have told you that short trick na to check vector space. Firstly, it should be a vector space. Then only it will be a vector subspace na.
Mm-hmm. Okay.
It is not a vector space because
Because closure property and
closure property fails.
yes.
Q complement to real will not go to Q complement. If I take any irrational number 1 by 2 into some irrational, I can take a irrational number from real numbers also, then it will be 1. It is not a irrational number. Now, how to test a subspace? First thing, W with respect to addition operation should be an abelian group. Second thing, field with respect to addition and multiplication. F with respect to multiplication and addition should be a field. Third thing, W cross F should go into W. Fourth, all the 4 properties should satisfy. Now a small theorem to check W is a subspace of V over F if and only if alpha beta 1 plus alpha W1 plus beta W2 belongs to W for all W1 W2 belongs to W and for all alpha beta belongs to field. So if this condition is satisfied, then I will say that W is a subspace of V. W is a subspace of V if W is closed under addition and scalar multiplication. Now a small trick to check a subspace. Firstly, it should have additive identity. Second thing, linearity. This trick is also valid under only usual operation. If operation is unusual, then I cannot apply this trick. Let us discuss some examples for this. Vector space is R square over R. W is x comma y belongs to R square such that x is equals to 0, y belongs to real numbers. So if I apply this theorem, then I will take two elements w1 as x1 comma y1. Here x1 will be 0 by definition of this w. w2 will be x2 comma y2 belongs to w. This implies x2 is 0. So alpha w1 plus beta w2. This will be alpha x1 comma y1 plus beta x2 comma y2. This will be alpha x1 plus beta x2 comma alpha y1 plus beta y2. x1 is also 0, x2 is also 0. So this will be 0 comma alpha y1 plus beta y2. This clearly belongs to w. So w is a subspace of V. Or I can apply the trick also. Here additive identity 0 comma 0 belongs to W na, and also it is linear. So W is a subspace of V. Any doubt till here?
No, ma'am.
V is equals to R square over R. W is equals to x comma y belongs to R square such that x plus y equal to 0. Again, I can take two elements w1 as x comma y, x1 y1 belongs to w. This implies x1 plus y1 is 0. w2 as x2 comma y2 belongs to w. This implies x2 plus y2 is 0. Now alpha w1 plus beta w2. Alpha x1 comma y1 plus beta x2 comma y2. So alpha x1 plus beta x2 comma alpha y1 plus beta y2. This can be written as alpha x1 plus y1 plus beta x2 plus y2. Now x1 plus y1 is 0, x2 plus y2 is 0. So this will be 0 and 0 belongs to w. This implies alpha w1 plus beta w2 belongs to w. So w is a subspace of V. Or we can apply trick also. 0 comma 0 belongs to this w and also it is linear. Third example, V is equals to R square over R. W is equals to x comma y belongs to R square such that x is equals to 1. Tell me whether this will be a vector subspace or not. You can directly apply a trick here.
So additive identity can't be applied because x equal to 1 is fixed.
W is not a subspace of V because 0 comma 0 does not belongs to W because x equal to 1. This value is fixed now. V is equals to R square over R. w is equals to x comma y such that x is equals to y square. Tell me whether it is a subspace or not. First property is additive identity.
That exists actually.
Additive identity exists.
Hmm. But the linearity condition, I'm checking.
Linearity condition will fail, na? Y square term is present,
Yes.
so it is not linear. Or one more thing can be seen. If I take two elements as 1 comma 1 belongs to w, na? Because x is 1 and y is 1, so x is equals to y square. This condition is being satisfied. So 1 comma 1 plus 1 comma 1, this is 2 comma 2, but this term is not present in this w, na? Because x is 2 and y square it is 4. 2 equal to 4, not possible. So this does not belongs to w. This means closure property fails. Let V be the real vector space of all functions f from R to R, which of the following sets of functions are subspaces of V. First part, all f such that fx square is equals to fx square. Now here, if I apply that theorem, then it will be better, no? Means alpha w1 plus beta w2 should belongs to w. So let w is equals to f belongs to vector space V such that fx square is equals to fx square. Now here I can take two functions from w, then fx square is fx square, gx square is equals to gx square. Let a comma b belongs to real numbers, two scalars from the field f. Then af plus bg x square. This will be af x square plus bg x square. Now constant can be taken outside. A fx square plus b gx square. This will be a fx then its square plus b gx square. Also AF plus BG x square, because this condition should be satisfied. That's why I am taking this also. So this will be AFX plus BGX square. This will be A square fx square plus BGX square plus 2AB fx into gx. Now AF plus BG x square is not necessarily equal to AF plus BG x square, which means that AF plus BG is not a member of this W, so W is not a subspace of V. Second part, all F such that F0 is equals to F1. Let W is equals to F belongs to this vector space P such that F0 is equals to F1. I will take two members of this W, then F0 is equals to F1 and G0 is equals to G1, and two scalars from the field real. So AF plus BG 0 is equals to AF0 plus BG0, and F0 is equals to F1 plus BG1. So it can be written like this: AF plus BG1. Given condition is satisfied. Therefore, by definition of W, AF plus BG belongs to W. This means W is a subspace of V. All F such that F3 is equals to 1 plus F minus 5. Try this question and tell me whether it is a subspace or not.
It is not.
Reason?
The thing is, we are not getting 1. We are getting A plus B. 1 plus this linearity condition is not coming.
W set is f belongs to f belongs to B such that f3 is equals to 1 plus f minus 5. So let f comma g belongs to W, then f3 is equals to 1 plus f minus 5 and g3 is equals to 1 plus g minus 5. So AF plus BG3. This will be A F3 plus B G3. And F3 is 1 plus F minus 5 plus B 1 plus G minus 5. It can be written as A plus B plus AF plus BG minus 5. And I wanted that it will not be equal to 1 plus AF plus BG minus 5. Means it is not necessarily equal to this. So this condition is not satisfied. AF plus BG does not belong to W. This implies W is not a subspace of V. Or one more thing can be applied here. By trick, additive identity is not present in this. It is not present in
Yes, ma'am.
all F such that F minus 1 is equals to 0.
This is subspace.
Yes. A into 0 plus B into 0. This is 0. So A plus G belongs to W. So W is a subspace of V. All F which are continuous.
This is also a subspace.
Hmm. F belongs to V such that F is continuous. So simply I can see that if F and G are continuous functions and A comma B belongs to real numbers, then AF plus G is also a continuous function. This implies W is a subspace of V. Next example. Consider a homogeneous system of m linear equations in n unknowns x1, x2 up to xn over a field K. Homogeneous system can be written as a11x1 plus a12x2 so on till a1n xn equal to 0. a21x1 plus a22x2 so on till a2n xn equal to 0. Then the solution set W is a subspace of the vector space Kn. This I need to prove. Now this system is equivalent to Ax equal to 0. No? A is the coefficient matrix I have discussed in system of equations. So first thing, additive identity. A into 0. This is 0. Here 0 is the 0 vector. Where 0 is 0, 0, 0 transpose. Now additive identity is present. Next thing, linearity property is to be checked. Now suppose u comma v are vectors in this vector space W, which means, and W is the solution set, na? Means u and v are solutions of the system. So as they are solution of the system, so it will satisfy this AU equal to 0 and AV equal to 0. Now for any scalars, A and V belongs to K, we will have A AU plus BV is equals to, constant can come outside, A AU plus B AV. AU is 0, AV is 0. So this will be 0. So AU plus BV is a solution of the system, which means AU plus BV belongs to W. Thus, W is a subspace of Kn. Any doubt?
No, ma'am.
Okay. Next example. Let Ax equal to B be a non-homogeneous system of linear equations in n unknowns over a field K. Then tell me whether this will be a subspace or not. solution set of the system.
It can be the solution because 0 0 तो exist करेगा if we take b 0. So
0 0
it
will
can.
not, 0
Yes,
0 will not
subspace
exist.
तो होगा ही. Subspace तो होगा अगर हम
Ax equal to b.
इसको.
This is non-homogeneous, means b is non-zero, na?
b is non-zero. तो फिर इसमें additive identity exist नहीं करेगी.
This is not a subspace of Kn because additive identity is absent. Is R square a subspace of R cube?
It will not be.
Reason?
सी ऑर्डर्ड पेयर जब हम करेंगे इसमें तो वो आर क्यूब का तो आएगा नहीं ना, वो तो आर स्क्वायर का ही होगा अगर हम लेंगे तो.
If we will
तो
take
फिर इसे क्लोजर प्रॉपर्टी ही नहीं सेटिस्फाई होगी इसमें तो.
if we take any ordered pair of this R square, then this can be written as a comma b comma 0 in R cube, and they are distinct elements, so it cannot be subspace. If a vector space V is the set of all real valued continuous functions over the field of real numbers R, then show that the set W of solutions of the differential equation two d square y upon dx square minus 9 dy upon dx plus 2y equal to 0 is a subspace of V. Now here W is y such that 2 d square y upon dx square minus 9 dy upon dx plus 2y is equals to 0, where y is fx because W is a set of solutions of this differential equation. Now, as this is a homogeneous differential equation, so y equal to 0 is a solution of this differential equation. This means 0 belongs to W, which means that W is non-empty. Now I will take two members of W, then 2 d square y1 upon dx square minus 9 dy1 upon dx plus 2 y1 equal to 0, 2 d square y2 upon dx square minus 9 dy2 upon dx plus 2 y2 equal to 0. Now suppose a and b are scalars from real numbers, then W is a subspace if a y1 plus b y2 belongs to W, which means that a y1 plus b y2 is a solution of the given differential equation. So 2 d square upon dx square a
इसको
y1
हम डायरेक्टली भी बोल सकते हैं कि बिकॉज इफ टू आर द सॉल्यूशन देन एनी लीनियर कॉम्बिनेशन इज आल्सो द सॉल्यूशन ऑफ द सिस्टम.
वैसे भी बोल सकते हैं या फिर प्रॉपर्टी चेक करके भी बोल सकते हैं. minus 9 d by dx a y1 plus b y2 plus 2 a y1 plus b y2. Now this can be written as 2a d square y1 upon dx square plus 2b d square y2 upon dx square minus 9 a dy1 upon dx minus 9b dy2 upon dx plus 2a y1 plus 2b y2. Now I can take a common and write 2 d square y1 upon dx square minus 9 dy1 upon dx plus 2y1 plus b common 2 d square y2 upon dx square minus 9 dy2 upon dx plus 2y2. And by taking 1 and 2 into 0, so a into 0 plus b into 0 is 0, which means that a y1 plus b y2 is a solution of the given differential equation. So W is a subspace of B. Now try this question. This is from June 2015 question. Which of the following are subspaces of the vector space R cube? A part x, y, z such that x plus y is 0. B part x, y, z such that x minus y is 0. C part x, y, z such that x plus y is 1. D part x, y, z such that x minus y is 1. This is part C. Here you can simply apply the trick, na?
So this is only T and B.
Yes, because in C and D, additive identity is not present. The set V equal to x comma y belongs to R square such that xy is greater than 0 is a part a vector subspace of R square, not a vector subspace of R square, since every element does not have an inverse in V. C part, not a vector subspace of R square, since it is not closed under scalar multiplication. Not a vector subspace of R square, since it is not closed under vector addition.
Is option C.
reason?
It is not closed under scalar multiplication. See. 0 0 तो एग्जिस्ट करता है, तो आइडेंटिटी तो है एडिटिव, बट इट इज नॉट लीनियर एक्चुअली, एक्स वाई है ना, तो
If you are saying that it is not closed under scalar multiplication, then you must have taken any example.
just if I take x minus 1 y1, then it will be negative, it will not be positive.
I cannot take this example.
So alpha xy plus beta xy, if I take alpha beta xy, alpha xy,
Or if I take simply this element minus 1 comma minus 2, then minus 1 into minus 2, 2, which is greater than 0. This condition is satisfied. Or you are saying that it is not closed under scalar multiplication. Alpha belongs to real numbers. I can either take alpha greater than 0, alpha 0, or alpha less than 0. If alpha is greater than 0, say alpha is 1, then also this is satisfied, na?
But negative can you be satisfied?
Alpha less
If
than
I take
0,
alpha is negative, then it will not satisfy.
alpha negative, alpha minus 1. So minus 1 and minus 1 comma minus 2. Then this minus 1 sign will be multiplied in this, na? Then it will be 1 comma 2. Again it is satisfied. Product of these two numbers should be greater than 0, na?
Yes.
So scalar multiplication is satisfied. But addition, vector addition will not be satisfied. If I take another element as 0 comma 4, then minus 1 comma minus 2 plus 0 comma 4. This is
minus 1 and minus 8. Minus 1 and 2.
And their product is less than 0.
Minus 2. Okay.
So this does not belongs to V, means closure property fails.
Got it.
So answer will be option D. Let M be the vector space of all 3x3 real entries and let A is equals to 2 0 0 1 2 0 0 0 3. Which of the following are subspaces of M? Part C. A part, X belongs to M such that XA is equals to AX. B part, X belongs to M such that X plus A is equals to A plus X. C part, X belongs to M such that trace of AX is equals to 0. D part, X belongs to M such that determinant of AX is equals to 0. Try this question.
It is A and B.
And what about C?
C is trace of AX equal to 0 and trace of A matrix is not 0.
Okay, let us check all the options one by one. So in first option, x belongs to M such that xa is equals to ax. So how you have checked this? By applying the definition. If I take two members of this M and alpha beta belongs to real numbers, alpha x plus beta y M is equals to alpha a. Alpha xa, alpha ax plus beta ay. I can take a common, alpha x plus beta y. So alpha x plus beta y belongs to S1. So S1 is a subspace of M. Option A is correct. Similarly, option B, S2 is equals to x belongs to M such that a plus x is equals to x plus a is equals to a plus x. Let x comma y belongs to S2 and alpha comma beta belongs to real numbers. Alpha x plus beta y plus a is equals to a plus alpha x plus beta y, because addition of matrices is commutative. Which means alpha x plus beta y belongs to S2. So S2 is a subspace of M. Option B is also correct. Option C, S3 is x belongs to M such that trace of AX is equals to 0. Let x comma y belongs to S3, alpha beta belongs to real numbers. Now trace of alpha, trace of A, alpha x plus beta y. This will be, there's a property that the constant will come outside of this trace. So alpha trace of AX plus beta trace of AY, and this is 0, this is 0. So alpha x plus beta y belongs to S3. S3 is a subspace of M. Now is it clear? C is also correct. Now option D.
Yes, sir.
So option D is correct or not? X belongs to M such that determinant of AX is 0. This is not correct. This is not a subspace. So I need to take counter example. So if I take X as 1 0 0 0 0 0 0 0 0 and Y as 0 0 0 0 1 0 0 0 1. AX, what was my A? 2 1 0 0 2 0 0 0 3. So this will be, first entry will be 2 and rest will be 0. Similarly, AY, 0, 1, 0, 0, 2, 0, 0, 0, 3. Determinant of AX is 0 and determinant of AY is also 0, which means X and Y belongs to S4. But AX plus AY is equals to A. I can take a common X plus Y. So this will be A 2, 0, 0, 1, 2, 0, 0, 0, 3 X plus Y. And this is 2, 1, 0, 0, 2, 0, 0, 0, 3. And what is determinant of AX plus Y? 2 into
Is it 12?
what are you saying?
12.
12, sorry. Non-zero means X plus Y does not belongs to S4. Closure property fails. So S4 is not closed under addition. So S4 is not a subspace of M. So option D is also wrong. Answer will be ABC. Now one small thing. Algebra of subspaces. The intersection of any two subspaces W1 and W2 of a vector space VF is also a subspace of VF. Means if W1 and W2 are two subspaces of V, then their intersection W1 intersection W2 is also a subspace of V. Second thing, the union of two subspaces is a subspace if and only if one is contained in the other. Which means if W1 and W2 are two subspaces, then W1 union W2 is a subspace of V if and only if either W1 is contained in W2 or W2 is contained in W1. Now next is linear combination. let V over F be a vector space if V1, V2, so on till Vn. These are vectors in this vector space V. Then any vector V equal to alpha 1 V1 plus alpha 2 V2, so on till alpha n Vn, where scalars belongs to field F, is called a linear combination of the vectors V1, V2, so on till Vn. So I have taken a set of vectors in this vector space V. Any vector can be represented as a linear combination of these vectors. So this is the definition of linear combination. Now next is linear span. Let Vf be a vector space and S be a non-empty subset of V. Then the linear span of S is the set of all linear combination of finite elements of S and is denoted by Ls, which means that in the linear span all the possible linear combination of the finite elements of S will be there. So linear span is alpha 1 V1 plus alpha 2 V2, so on till alpha n Vn, such that all the alpha i's belongs to field I is from 1 to n and V1, V2 up to Vn. These are finite elements of S. The linear span of any subset S of a vector space Bf is a subspace of V generated by S, that is Ls is equals to this. So linear span is a subspace of V which is generated by S, and generator is denoted like this now. Let S be a subset of a vector space V span of S is a subspace of V which contains S. Means span of S is a subspace of V, span of S is a subset of V and which contains S. S will be contained in the span of S now because S contains finite elements and span of S contains all the possible linear combinations of these finite elements of this set S. So span of S is a subspace of V. Second thing, if W is any subspace of V containing S, then span of S is contained in W. Now, span S is also a subspace of V. W is also a subspace of V. But there is a restriction on this span of S. In this span of S, all the possible linear combinations of this set S is there. So, whenever there is a restriction on any set, then that set will be a smaller set, na? Is this clear?
Yes, ma'am.
Okay. Now let us discuss some examples. S1 equal to 1 0 0 1 over reals, it is field. Now firstly tell me whether this is a subspace or not. You can directly see now. For subspace, first thing you need to check is additive identity. Here additive identity is 0 0. It is not present in this na. So S1 is not a subspace of R square. Vector space V is R square. Is this clear?
Yes, ma'am.
Now I need to form all the possible linear combinations of this S1. It will be framed like this: alpha into 1 comma 0 plus beta into 0 comma 1 such that alpha beta belongs to real numbers. So this will be alpha comma beta. Alpha and beta are real numbers. So what will be this? Complete R square. All the ordered pairs will be there, na? So spanning set of S1 is a subspace of R square over R. Because I told you that R square over R is a vector space, na? We have discussed this in the previous class.
Yes, ma'am.
So this example tells that S1 was not a subspace, but then also linear combination of S1. All the possible linear combination of S1 means spanning set of S1 is a subspace of R square over R. Similarly, subset S as 1 0 0 0 1 0 0 0 1 of V3F. This is RQ over field real numbers. Now this generates the entire vector space V3F, that is, spanning set of S is complete V. If ABC is any element of this V, and V is R cube, then ABC can be written as linear combination of elements of this S, A into 100 plus B into 010 plus C into 001. So ABC belongs to the spanning set. Also, this spanning set is contained in V na, it is contained in R cube. Hence, spanning set is equal to V, because spanning set is a subspace of V na. Next example. The subset containing a single element 100 of the vector space generates the subspace which is totality of the elements of the form A00. Now, this is a subset containing a single element. Means in this set S, a single element, this is present. So what will be the spanning set? Linear combination of alpha into 100, because only single element is there and alpha belongs to field. So alpha 0, 0. I can take alpha here. It is a scalar only. Is this clear?
Yes, ma'am.
Now next is linear sum of two subspaces. Definition: let W1 and W2 be two subspaces of the vector space Vf, then the linear sum of the subspaces W1 and W2 denoted by W1 plus W2 is the set of all sums W1 plus W2 such that W1 belongs to capital W1 and small w2 belongs to capital W2. Thus, W1 plus W2 is W1 plus W2 such that W1 belongs to W1 and W2 belongs to W2. So we will have two subspaces of the vector space V. Then the linear sum of W1 plus W2. It can be represented by this W1 plus W2, where W1 belongs to capital W1 and W2 belongs to capital W2. Now, W1 plus W2 is a subspace of VF. Second thing, W1 plus W2 is equal to generator of W1 union W2. Means that is spanning set of W1 union W2 is W1 plus W2. Now a question on this only. June 2012 question. Part C. Let V1, V2 be subspaces of a vector space V, then which of the following is oblique R necessarily a subspace of V? A part V1 intersection V2, B part V1 union V2, C part V1 plus V2, D part V1 minus V2. Tell me which is the subspace of V.
A and C.
I have already told A. Intersection of two subspaces is a subspace of V.
Hmm.
B is wrong because it is a subspace if and only if either V1 is contained in V2 or V2 is contained in V1. And C part, linear sum is also a subspace of V. What about D?
See, V1 minus V2 will also contain in V, but V1 minus V2 is contained in V1. So, can't say.
V1 and V2 are subspaces, so
Yeah.
additive identity will be present in both,
Hmm.
but 0 does not belongs to V1 minus V2. So V1 minus V2 is not
Not.
a subspace of V. Because if I say that 0 belongs to V1 minus V2, then I will say that 0 belongs to V1 and 0 does not belongs to V2. But V2 is a subspace, so additive identity is already present in this. So 0 does not belongs to V1 minus V2. That's why it is not a subspace. So answer will be A and C. Let V be vector space of all n cross n real entries over field R then which of the following sets are subspaces of V? A part, the set of upper triangular matrices. So firstly tell me, what is the upper triangular matrix?
The entries below diagonal, main diagonal is 0.
Yes. So I can simply see like this without any calculation. This is the upper triangular matrix, another upper triangular matrix. This will be also upper triangular matrix. So it is closed under addition. Similarly, scalar multiplication, alpha into upper triangular matrix. Below entries are 0. So alpha will come outside. So scalar multiplication is also satisfied. So it is a subspace. B part, the set of lower triangular matrix. What is a lower triangular matrix?
The entries above the main diagonal is 0.
Hmm. It is closed under addition, and similarly it can be shown that it is closed under scalar multiplication. So it is also subspace. The set of scalar matrices, or before that, set of diagonal matrices. What is a diagonal matrix?
We have entries on the main diagonal and other entries are 0.
Hmm. If I have a 3 cross 3 matrix, only entries will be on this diagonal, rest will be 0. So this will be a subspace or not?
This is a subspace.
The set of scalar matrices. What is a scalar matrix?
It is a diagonal matrix
Hmm.
which has all main diagonal entries same.
Hmm. So it is also a subspace. The set of tri-diagonal matrices. So if it is a matrix, then this one is principal diagonal or main diagonal. Diagonal above principal diagonal is super diagonal, and diagonal below this principal diagonal is sub diagonal. So it is also a subspace because it will be closed under addition and scalar multiplication. the set of all non-singular matrices. Tell me whether it is a subspace or not.
Um, it it is it can be because some of the non-singular matrices may be singular, or it is always non-singular. The sum of the determinants. Mm, not
Clearly,
getting it.
clearly 0 is not present in this na if it is W. Additive
Yes.
identity is not present, so it is not a subspace.
Okay. Yes. Yes.
The set of all singular matrices.
It is a subspace.
It is also not a subspace. We have already discussed na in that question determinant of Ax equal to 0.
Yes. Yes.
It
Right.
was a singular matrix only na.
Mm-hmm.
So what will be the problem in this? That if I take A matrix as 1 0 0, B matrix as 0 0 1. Clearly determinant of A is 0, determinant of B is 0, but determinant of A plus B is non-zero. So A plus B will not belong to W. So it is not a subspace. Similarly, if W is a set where A belongs to V such that trace of A is 0, then it is a subspace na. And if I take W as A belongs to V such that trace of A is not equal to 0, then it is a subspace or not?
It is not a subspace. 0 0 is absent.
Hmm. Because additive identity is absent. And what will be additive identity in this?
Zero matrix.
Yes. Next, the set of symmetric matrices.
It is a subspace.
What is the definition of symmetric matrix?
A transpose equal to A.
Hmm. This is a subspace of V over R, because this will be like this: Aij is equals to Aji. Transpose will be taken. So this implies Aij minus Agi is equals to 0 for all I comma j. This means that it has additive identity also, it will be linear also, and if I check those conditions, means by definition, then A plus B transpose, this is A transpose plus B transpose, and alpha A transpose, this is alpha A transpose. So all the conditions are satisfied, so it is a subspace. Next is the set of skew symmetric matrices.
It is not a subspace.
Reason?
Um,
Skew symmetric matrix is given by A
A
transpose.
transpose equal to minus A.
Means
Oh,
Aij is equals to minus Abi.
yes.
Additive identity will be present in this. It is linear also. So it is a subspace.
Yes, ma'am.
So in this question, more than one option can be correct. Let V be the set of 2 cross 2 matrices A11, A12, A21, A22 with complex entries such that A11 plus A22 equal to 0. Let W be the set of matrices in V and A12 plus A21 conjugate is equals to 0. Then under usual matrix addition, and scalar multiplication, which of the following is are true? A part, B is a vector space over C. B part, W is a vector space over C. C part, V is a vector space over R. W is a vector space over R.
S, A, C, and this one, W, B, sorry. A, B, C.
AC is correct. And answer is ACD. B is not correct. So let us see the
But it
solution.
is written conjugate, no? W is a set of matrices B and A12 plus A21. अच्छा वो B तो complex ही है. Conjugate.
So B is a set of 2 cross 2 matrices with complex entries such
So
that
complex entries.
diagonal
Okay.
entries are 0, and W is a set of matrices in B, and A12 plus A21 conjugate is 0. So in
Yeah,
A1,
diagonal entries, some of the diagonal entries is 0, no? But diagonal entries are not 0. Some of diagonal entries.
sum of diagonal entries are 0. Let A is equals to A11, A12, A21, A22. B will be B11, B12, B21, B22 with sum of diagonal entries equal to 0. So that A and B belongs to vector space V. A and B belongs to set V because we need to check vector space. Now let alpha and beta belongs to complex numbers because entries are from complex numbers. So that alpha A plus beta B. This will be alpha A11 plus beta B11, alpha A12 plus beta B12, alpha A21 plus beta B21, alpha A22 plus beta B22. So alpha A11 plus beta B11 plus alpha A22 plus beta B22. I am taking sum of diagonal entries. So alpha common A11 plus A22 plus beta common B11 plus B22. This is also 0. This is also 0. So alpha A plus beta B belongs to V, which means that V is a subspace of vector space of 2 cross 2 matrix whose entries are from complex numbers over C. So V is a vector space over C. So option A is correct. Now option B. Option B is saying that W is a vector space over C. So it is not true, first of all. So for this I need to check any example. If I take matrix A as 0 iota iota 0, so that A12 plus A21 conjugate. A12 is iota plus A21 iota conjugate iota minus iota. This is 0. This is being satisfied, which means that A belongs to W. Now scalar multiplication. If I take any scalar iota for complex numbers from complex numbers, so iota into A. This is 0 minus 1 minus 1 0. Then A12 plus A21 conjugate minus 1 minus 1. This is minus 2, not equal to 0. So scalar multiplication property is not satisfied. So W is not a subspace over C, B part is wrong. C part was V is a vector space over R. It can be similarly checked na. In A part, I have proved that alpha A plus beta B belongs to V for all alpha beta belongs to complex numbers. And I know that real numbers is contained in complex numbers. So alpha A plus beta B belongs to V for all alpha beta belongs to real numbers. So V is a vector space over R. C part is correct. Last part, W is a vector space over R. Now take two matrices. B equal to B11, B12, B21, B22. A12 plus A21 conjugate is equals to 0. B12 plus B21 conjugate is equals to 0. Such that A comma B belongs to W. Let alpha beta belongs to real numbers. This implies alpha A plus beta B. This will be alpha A11 plus beta B11, alpha A12 plus beta B12, alpha 21 plus beta B21, alpha A22, alpha A21 plus beta B22. So alpha A12 plus beta B12 plus alpha A21 plus beta B21 conjugate. Now we are talking in real numbers. So this will be real only na. Alpha A12 plus beta B12 plus alpha A21 plus beta B21. So I can take alpha common. A12 plus A21 plus beta B12 plus B21. So this will be 0 only, because here also A21 conjugate will be 1 second. This will be like this, alpha A21, or I can break the conjugate. Alpha conjugate A21 conjugate plus beta conjugate B21 conjugate. So alpha A12 plus beta B12. Alpha beta were real numbers, but the entries are from complex numbers. So alpha A21 conjugate plus beta B21 conjugate. I can take alpha common. A12 plus A21 conjugate plus beta B12 plus B21 conjugate. So this is also 0. This is also 0. So alpha A plus beta B belongs to W. So W is a sub vector space over R. Option D is also correct. So answer for this question is A, C, D. Is it clear?
Yes, ma'am.
Okay. So subspace topic is over till here.